then a Harvard postdoctoral fellow and also a Harvard junior faculty before moving to Berkeley as a faculty member, and she's affiliated with LBNL as well as the Atlas experiment. So thank you, Marjorie, for joining us today. Please go ahead with the seminar.
Well, thanks very much. It's a pleasure to be here, and I'm just sorry that everything has to be over Zoom, but it's great to be able to give this talk. So the title of my talk is Constraining Beyond the Standard Model Physics Using Standard Model Measurements at the LHC. Now, I have to say that when I joined the LHC, it never occurred to me that in 2021 I would be giving a talk with this title. When people asked me why I joined the LHC, because of course it's very far from Berkeley, it's a 9-hour time difference, it's a long commute. I knew I wanted to do it because the LHC was the one place where you could really probe this beyond the standard model physics as much as possible because of the high available energy. Originally, I had been on the SSC, which was supposed to be the high energy accelerator in the US. And when the SSC project was canceled, it was clear that the LHC was the place to be. But when people asked me, what are you going to do at the LHC? I was very clear about it. I said, I'm good at measuring the parameters that help us to understand the breaking of SUSY. So I was convinced when we turned on the LHC, we would see supersymmetric particles right away, and that our program was going to be one where we were doing precision measurements, but it was precision measurements to understand the sources of SUSY breaking. Now, as you all know, the first 2 runs of the LHC haven't seen any evidence for supersymmetry. That doesn't, it's beyond the standard model. There clearly needs to be for a lot of reasons, and I'll talk about some of them today, but it means we have to go back and use other techniques in order to probe that. And so that's really what I'm going to be talking about today. Okay, so the outline is I'll start with a brief introduction to set the stage, to talk about the type of measurements we're talking about. I'm not going to have a chance to say a lot about the Large Hadron Collider or the experiments, but I'll just flash a couple. And the main topic of this, again, is looking for new physics. So I'm going to concentrate on 2 areas, probing new physics from constraints on virtual corrections. And there I'm going to talk about measuring the mass of the W and the mass of the top. And secondly, talking about Diboson production and the search for anomalous couplings. Here we have to understand that we can have both strong and electroweak production, and they have different characteristics. How we can use the measurement in order to constrain both triple and quartic coupling constraints, and then about vector boson scattering with an emphasis on the channels that are sensitive to electroweak processes, and then I'll have conclusions. You can see from my outline that I'm not going to talk about the Higgs at all. That's not because the Higgs isn't important. It's of course a very central, and I think a lot of the new physics that we're going to be looking for at the LHC we're likely to be able to probe using precision measurements involving the Higgs. But the story of the Higgs is a very complex one. If I wanted to concentrate on that, it would really take the whole seminar. So I decided to talk about the other issues, places where we can do the searches. And presumably at some point in the future, your seminar series can get someone who's very involved in the constraining Higgs measurements, and that, as I say, is a seminar unto itself. But I did want to just mention it because, of course, it is a really essential part of the LHC program. Okay, introduction. We all know that the standard model is incredibly successful at describing particle physics data. There's almost no data that we can't describe within the standard model. The one exception, of course, is neutrino mass. The standard model has massless neutrinos, and it only has left-handed neutrinos, no right-handed ones. We don't really understand the nature of neutrino mass, and there's a large experimental program to do that, but whatever causes that mass is a part of beyond the standard model that really is going to be probed in ways other than the LHC. With the discovery, the standard model is now complete. Particles that are part of the standard model, their charges and their couplings. But there are a lot of this isn't the whole story. The list of unanswered questions really hasn't changed very much in the last 30 years. We haven't found the answers to all those questions, but it doesn't mean that the questions themselves are any less important than they were when we first posed them before the LHC turned on. We want to know, does particle physics provide a source of dark matter? It could be supersymmetric particles. The lightest symmetric particle is a classic candidate for dark matter. It could be some other kind of dark matter that also has a particle nature that could be produced in something like the Large Hadron Collider. We want to know why gravity is so much weaker than the other forces. Presumably, there's a grand unified theory that's going to take over. And the question is there any evidence that we can see for that theory in the experiments we do? Why is there so little matter in the universe? Studies of matter versus antimatter asymmetries for a long time were dominated by A plus minus, and although I'm not going to talk about them today, I think the LHCb experiment has shown that hadron collisions can play a very important role in the question as well. Are there extra space-time dimensions? Is that part of the reason why gravity looks the way it does? And why are there 3 generations of quarks and leptons? The answer to any of these questions would revolutionize our view of the world. Models to try and provide answers to these questions, but at the moment, without any hints from the data, we don't know which direction is the most appropriate to move. Okay. So the search for physics beyond the standard model can really be done in 2 ways. First is what I call direct searches. That's the case for bumps in invariant mass or in excess of events. Most of these searches now are spaced, and we have searches that focus on looking at signatures that would be found in supersymmetric models, places where you have extra gauge bosons, or complicated Higgs sector. There's no reason to believe that we're not in a model that has 2 Higgs doublets, for example. Leptoquarks, you can put your favorite model here. But sort of the generic way those searches are done is shown in this plot on the top. I just happened to an atlas plot that searches for heavy particles of B quarks that then form B jets. And you can see that there's typically a large background, which is unfortunately consistent with data. And then you can see 2 bumps that are what you would expect with different masses for potential beyond the standard model particles. Now, these direct searches, of course, have the advantage that if you see something that's very concrete, you know it's new physics, and it's very often easy to map it onto a specific model. And once you've seen one of those bumps, then it gives you a hint of what other channels to look at in order to confirm or refute that A, the signal is real, and B, it belongs to the model that you want. So I've always thought that if you can do it, direct searches are the best, but they don't always allow you to proceed, because if you don't see anything in the direct searches, then you need to know another way. So the second approach is using precision standard model measurements. And here, for a lot of reasons, the poster child really is G-2. So G-2 is a measurement that's been essential for understanding particle physics since the 1950s. When quantum electrodynamics was first developed, it was calculations such as G-2 that convinced people that renormalization actually made sense, that the idea of taking the difference between 2 infinities and getting a finite non-zero number was reasonable. And the ability to do these calculations at high precision was a demonstration that quantum field theories were appropriate. G-2 has been in the news a lot lately because, of course, there's a new measurement from Fermilab that appears to disagree with the standard model calculations. Now, we have to be a little careful about this. There's 2 sets of standard model calculations, one of which uses lattice gauge theory and the other which uses calculational techniques involving loops of hadrons, and those 2 differ. If you use at least the latest lattice gauge theory calculations, it comes closer to the G-2 measurements. So I don't want to say anything here about whether or not I believe this particular discrepancy is indication of new physics. That's something that I don't think we'll know until we understand better the disagreement between the two theoretical methods of doing the calculation. But the message here is really that these kind of very precise measurements that are sensitive to loop corrections in the standard model have the potential to constrain or demonstrate the need for beyond the standard model contributions through loops. And it also shows you the potential disadvantages. You're very dependent on believing details of the calculations, while if you see a bump, you may argue about whether or not the theory gets the calculation of the rate of that bump right, but there's no question you've seen nothing new. So one of the hallmarks of these indirect measurements is very often you can't tell what new physics is causing the deviation, but on the other hand, it can provide you hints as to where else to look. So these two techniques are always going to be used, and playing them off against each other is important. Which one plays the dominant role changes as a function of time. When you turn on a new accelerator at a new energy regime, the direct searches clearly take precedence at the beginning because they have the potential to really see something quickly, and what you see is very unambiguous. If you don't see anything in the direct searches, then you roll up your sleeves and start doing the hard work to do the precision measurements. Okay, so what's the role of the LHC in this picture? Well, it plays an important role in both of those pieces. In terms of direct searches, because the LHC has the largest available energy, that means it can produce particles with large invariant mass. So that means you have sensitivity to states that you wouldn't be able to produce at lower energy machines. In the old days, there was always this interplay between E+ E- colliders and hadron colliders. We hope in the future that will happen again. At the moment, the hadron colliders have so much more energy that even when you take into account the fact that the partonic center of mass energy is much lower than the proton-proton center of mass energy, the achievable energies are much higher. We still aren't able to produce top quarks or Higgs bosons at E+ E- machines. Again, in the future, that may change, but it's clear that the hadron colliders really are the easiest place to do those direct searches. Another real advantage is that both strong and electroweak production is possible. If we look at the diagram where two partons interact, because we have gluons, quarks, and antiquarks in the initial state, we're sensitive both to strong production and electroweak production. So it really means that the hadron colliders can probe a full range of the possibilities for new physics. In terms of precision measurements, the high luminosity means you have large statistics. Precise measurements are only possible when you have high statistics, both because you need them for the statistical accuracy of your measurement, but also because in general, to get that precision, one needs to do very careful calibrations, and the samples that are used to do those calibrations scale with the amount of data as well. High energy probes short range scattering of massive particles. And so it means that at these high energy colliders, we can look precisely at processes where the cross sections for them occurring are zero or close to zero at lower energy machines. And finally, as I said before, studies involving the Higgs are unique to the LHC. And although I'm not going to talk about them today, one really has to say that's one of the major reasons for the next runs of the LHC is to really probe insightfully the couplings of the Higgs and to ask the question, is there really only one Higgs boson, or is the Higgs that we're seeing the first of a family of Higgs? There's could be evidence in looking at the couplings for the presence of other Higgs bosons as well. Okay. So just a couple of words about schedule at the LHC past and future. Now, of course, accelerator schedules are always a bit iffy. They change with time. And the last 2 years have made that even more so because COVID has been a difficult time for everyone and certainly has slowed down the schedule of the LHC as well. The schedule that I've printed here is from January of 2021. It's the latest schedule we have. I can't tell you whether it's real or not, but I think it's as close to real as anything we're going to see. The important point is that the LHC is divided into periods that are called runs, where data happens, and periods that are called long stops, which are shutdowns, where both the accelerator and the experiment upgrade themselves. Run 1 of the LHC had center of mass energies of 7 and 8 TeV, integrated luminosity of about 30 inverse femtobarns. Run 2 had integrated luminosities delivered of about 190, closer to 130 to 140 for most physics measurements, and was run at 13 TeV. We're just finishing with long shutdown 2. And when we come on, we don't actually know for sure what the energy is going to be. It depends on the training of the magnets, but it will be somewhere between 13 and 14 TeV. And that run will essentially double the statistics that we currently have. And then after that, there's long shutdown 3, which will involve the installation of the high luminosity components of the LHC, major improvements to the detectors as well as to the accelerators. The hope is to come on then at 14 TeV and to really just run continuously for a very long period of time in order to get total integrated luminosities that are factors of 20 more than what we've been talking about before that. So both the experiments and the accelerator will really be different in those days. So the main message from this is, while we have a lot of data at the moment, we're at the beginning of a very long campaign, and things that look data challenged now can be done in the future, we hope. Okay. So the 2 general purpose detectors at the LHC are Atlas and CMS. I've just put pictures of the 2 here. They're both large general purpose detectors, although the designs are different in detail. I would say that if you integrate overall processes, there's no evidence that either one is much better than the other in the aggregate. You know, you can look at individual measurements where one is better than the other, but the overall physics programs have about the same reach. Both were designed to have excellent electromagnetic calorimetry that was really optimized for the Higgs discovery and the need to look at Higgs to gamma gamma. Different choices were made. Atlas chose to go with a sampling calorimeter with very good spatial resolution. CMS went with a crystal calorimeter that had very good energy resolution. We know from the discovery of the Higgs that both of those were perfectly reasonable design choices. In both cases, there's strong ability to identify leptons and to separate the signal leptons from the background of hadron production. And both experiments have robust bus tracking that at the current time is really limited to the central region, the pseudo-rapidity range below 2.5. Both experiments are planning to extend the tracking range further into the forward direction before the high luminosity LHC. And the other important thing to note is that both experiments have large angular coverage, so they have good missing momentum resolution. And just a word of terminology, we always talk about missing energy, but of course what we really mean is missing transverse momentum, because you can't really talk about a scalar quantity, but we do use that terminology. Okay. So just the standard model landscape, where are we now? I grabbed this picture from Atlas, but CMS has, of course, a similar picture. And I think the important thing to see, first of all, is the dynamic range of the measurements that we need to make at the LHC. If we look at the cross sections of the processes that we're exploring, they go over 12 orders of magnitude. The fact that the standard model can address questions with 12 different orders of magnitude in probability is pretty amazing. And if you look at the agreement between the data and the theory, which is shown in the plot on the right-hand side, you can see that the data to theory ratios are close to 1 for almost all of the measurements. There are some of the measurements that still have significant uncertainties, but there's almost nothing that disagrees by more than 2 sigma between the data and the theory. Given the number of measurements that have been made, that's pretty amazing. And you might almost ask, are the experiments overestimating their uncertainties? You'd expect, given how many measurements we've seen, to see a few more deviations just due to statistical fluctuations. Okay. In terms of direct searches, I don't expect anyone to be able to read these slides. It's just to show you the range of things that we can do with the LHC. Here's a summary of the kind of searches you can do for a variety of supersymmetric models. And you can see that the limits that we set really are very dependent on the channel. But in sort of a typical case, we're reaching the scale of masses of about a TeV. And that's really the range that one would hope to reach at the LHC. And again, in the old days, we all expected to see something in one of these searches by this point. At the moment, everything we have are limits, unfortunately. In addition to SUSY searches, there are many other exotic searches. I don't have time to present all of them. I've just chosen to show here the searches for new heavy particles. And here again, there's a very wide range of models. And while the individual limits vary, you can see that an overall mass scale of about a TeV is where we're ending up for the variety of the searches. Now, in terms of these sets of searches, we can ask how we're going to do as we get more data. Of course, when you do searches, in the end, you're going to be limited by the statistical power of the data. And as you get more luminosity, you can probe the higher energy reaches. So we do expect these searches to improve, in particular in the high luminosity LHC era. But being a bit cynical about run three is a factor of 2 in data. Given that we don't have any hints of a deviation at this point, unless you're talking about looking in a channel that we have not yet looked at, it's unlikely that you're going to see a 5 sigma observation from run 3 alone. Again, there are many channels that haven't been looked at yet. There's always the possibility that we will see something in those channels. So there is going to be a very robust search program in run 3. But I think really, if you're asking where we're going to have a lot more money in the searches, you're talking about the high luminosity LHC. Okay. So some perspective on what we've just seen. First of all, we really have to say the impressive with the standard model measurements. It's just amazing. I never would have thought we would see that level of precision over that many orders of magnitude. And it really is a very impressive intellectual achievement. Many of the direct BSM searches have been performed. They've been performed well, but so far all the results are negative. And so you might come away very discouraged, but I think that's really not the right attitude to take. The larger data samples available at the high luminosity LHC will extend the reach of the searches significantly. They'll push to higher mass. And in particular, cases where you have electroweak production, where the production rates are low, it will make an extremely large difference. And in many of these scenarios, the electroweak particles have lighter masses than the strongly produced particles. So there's a lot to be done there. In the case of supersymmetry, looking for the supersymmetric partner at the top, for example, is another area where I think there'll be a lot of new work to be done. In terms of the precision measurements, we really are in the early stages. In many cases, analyses using the full run 2 statistics that are already in the can and have been for several years is not complete. By definition, precision measurements require careful calibration. They tend to be much slower than some of the searches. And so we really are very far from having gone to the end of what we can do, even with the data that are currently available, never mind the run 3 and run 4 data. But fully exploiting the LHC data samples has required in the past and will continue to require significant technical advances. So in the remainder of this talk, I'll review some of these advances and then apply them to 2 cases. The first, constraining new physics from virtual corrections. There, the mass of the top and the mass of the W are the important parameters to measure. And second, constraints on anomalous couplings from vector boson scattering. So a word on technical advances. I have 2 slides, one on experiment and one on theory. And I've just highlighted a few things here. There are many other I could highlight. One thing I don't have on this slide, but I should call out, is the improvement in analysis techniques using machine learning and multivariant analyses. At the start of the LHC, although we did use some neural nets, I would say it was peripheral to a lot of the measurements. Now machine learning techniques are central to very much of what we do. Other areas where there have been significant technical advances are maintaining calibrations at high pileup. The way we get high luminosity is having large numbers of interactions per crossing. That means one has to be able to, in the data, pick out and understand events in the presence of many other collisions in the same bunch crossing. And in particular, for understanding the calibration of the calorimeters, where those additional particles from the other interactions will deposit energy in the calorimeter, requires new techniques. And I just picked an example here of CMS that shows that using pileup suppression, they can remove the dependence on the number of vertices on their calorimeter calibrations. A second experimental area where there's been a lot of work is improving trigger performance. There's a fundamental scale, in particular for the leptons and the photons, that one needs to keep, and that's related to the mass of the W and Z and the mass of the Higgs. If you want to maintain sensitivity to Higgs goes to gamma gamma and to samples that contain W's and Z's, you would like to keep your PT thresholds as low as possible. In the case of the jets, how important it is depends on the actual signal that you're trying to look at for beyond the standard model physics. But a lot of the improvements in the trigger performance have gone into tightening thresholds because you have rapidly falling input spectra. Being able to improve the resolution on those momenta can allow you to have much sharper thresholds on the trigger, which can improve your ability to select the events you want. An area that's been of interest for many years and is important mainly for the direct searches is identifying heavy boosted objects, cases where you have all of the decay products from a heavy thing in one energy cluster that you then have to turn into subclusters. And that's been an active area of experimental work. And then finally, again, at high momentum, reconstructing tracks in dense environments. And here I just show an example from Atlas where you can verify whether or not you have a problem with finding two tracks close together by using energy loss measurements in order to separate 1 versus 2 minimum ionizing particles and characterizing how often you lose a track in the detector. On the theory side, I would say, if anything, the advances have been even more impressive. And here again, I'm only highlighting a few possibilities. The existence of n-cubed LO perturbative theory calculations. In the old days, we never would talk about anything of that precision. There were almost no n-squared NLO calculations. And now more and more processes are being performed with these large level of perturbative calculations. This is extremely important in order to get the uncertainties due to the scale, because we know alpha sub s depends on scale, and the dependence on that scale goes down as we have more orders in perturbation theory. So precision measurements really depend on having these high order perturbative theories. There's also been significant, really major improvements in the treatment of parton showers, because many of the measurements that we care about now really depend on how well we can talk about the hadronization of quarks and understand in a systematic way how much our answer will change as we change that modeling of the non-perturbative part of QCD that we can't calculate from first principles. And so there's been a huge amount of work, not only tuning Monte Carlos, but coming up with mechanisms for plugging in alternative parton shower approaches so we can ask how much does our answer depend on that. As we go to higher and higher energies, electroweak corrections become more important. NLO electroweak corrections are a few percent at the TeV, and they're comparable in size to n-squared LO, that should be QCD corrections. And so being able to interleave electroweak and NLO corrections is really necessary. And then finally, how to deal with processes where you have multiple scales. Whenever you have more than one scale in the problem, you can end up with having large logarithms, and techniques in order to resum those large logarithms. So n squared leading log and additional resummations are an essential part of what we need to do. And the theory community has really done yeoman service in terms of making sure that all of these techniques are now available and can be used by the experimentalists. They don't just provide a plot in a paper and say, you have to look at the thing that I've plotted. They provide us with the tools where we can really apply these techniques to the cases we care about. Okay, so with that introduction, let me get more to the heart of the matter. And the first thing I said I was going to talk about was searches for new physics via virtual corrections. So the gauge sector of the standard model is constrained by 3 parameters. At lowest order, if you know the fine structure constant, G Fermi, and the mass of the Z, that's basically all you need to know in order to set all of the standard model parameters. And in particular, the mass of the W is constrained. You predict the mass of the W in terms of those 3 parameters. But of course, once we get to high order corrections, then we get corrections that modify this simple formula for the mass of the W and the relationship between the mass of the W and the weak mixing angle. The reason for those corrections can be both standard model and beyond the standard model. So on the left-hand side, we see the corrections that we expect in the standard model. There are 2 types. The loop corrections where W can turn into a TB bar, and then of course turn back into a W. Those corrections are quadratic in the mass of the top and the mass of the bottom. And corrections where the W can emit and reabsorb a Higgs, those are logarithmic in the mass of the Higgs. There, of course, can be similar loop corrections in BSM models, and what's shown on the right is what those would look like in the case where you have supersymmetric particles that can run around the loop. So the bottom line is that by making precision measurements of the mass of the top and the mass of the W, you can be sensitive to the presence of new particles in those loops. So what's the state of the art right now? The GFITR collaboration has done a remarkable job of taking all these measurements and understanding their consistency. And the first thing to know is that once the Higgs has been discovered, the standard model is over-constrained. So you can see on this plot the lines that correspond to different Higgs masses, because the mass of the W and the mass of the top relationship only depends logarithmically on the mass of the Higgs. In practice, you don't have to know the mass of the Higgs with incredible precision in order to know what ballpark you're in. On the other hand, both the top and the W mass are important, and we can see here the world average of the W mass and the top mass, and in the circles we can see the indirect measurements and the constraint you would get on mass of the W and mass of the top for 2 cases. One where you fit all the data without using the W, the top, or the Higgs mass. The second where you include the Higgs mass, but don't include the W and the top mass. And you can compare what you get for these indirect measurements of what you predict the W and top mass to be to what we see from the direct measurements. And you can see that they agree pretty well. There's really no evidence of a discrepancy once you take the uncertainties into account. The important thing from our point of view is that the LHC can, of course, improve on all 3 of those measurements, since the mass of the top, the mass of the Higgs, and the mass of the W will all be and have all been measured at the LHC. And looking at this plot, it's clear that the one that you want to focus on first is the mass of the W, because if you look at the ellipse, it corresponds to the case of the direct measurements, the green, the W mass has the largest uncertainty relative to what one needs in order to constrain the standard model. Okay, so the W mass, of course, was measured at LEP2, And then in a real tour de force, the Tevatron, both CDF and D0, did remarkably precise measurements of the W mass. And for a long time, people thought the LHC would not be able to compete, in particular because of the high level of pileup in the LHC. There was, in the old days, a feeling that it would never be competitive. Well, at this point, we've proved that that's not the case, although we're still in the early days of the story. The only W mass measurement at the LHC until recently was one from Atlas. There's now one from LHCb, which still has large uncertainties, but clearly is going to improve with time. And here I'm focusing on the LHC measurement from Atlas. It uses the low pileup 70 EV data and involved a huge effort to control systematic uncertainties using measurements of the Z boson as a control sample. It studied the two most sensitive observables, the transverse momentum of the lepton and the transverse mass of the lepton and the missing momentum. The method for finding the W mass is to make Monte Carlo templates where you vary the mass of the W in the template, and then you do a chi-squared minimization in order to see what W mass provides the best agreement. And you can see these are just two representative plots that the agreement between the data and the Monte Carlo is quite good. The background is low, although measuring the size of that background is still one of the significant systematic uncertainties in the overall measurement. The result from this measurement is a mass of the W that has an overall uncertainty of 19 MeV. That's comparable to the previous best measurement, which was done by CDF. And you can see that the statistical uncertainty in this measurement is small compared to the experimental systematic uncertainties and the modeling uncertainties. And in fact, the modeling uncertainties are dominant. Those uncertainties have to do both with the choice of parton distribution function, because that changes the longitudinal boost of the W, which affects the transverse mass distribution, and the transverse momentum of the W, because that affects the lepton PT. So you might say, okay, we're in trouble. Both of those uncertainties are what are dominating. How are we ever going to do better? And the answer is, well, because both the experimental uncertainties, which are set by how well one can calibrate, and the modeling uncertainties, which are set by the statistical uncertainty on the Z boson, which has lower statistics in the W, will improve as the amount of data goes up. So there is hope here, but controlling the uncertainties is going to be a challenge. And the ultimate goal from the people who are working on these measurements would be to try and get a precision below 10 MeV. Whether or not that will be feasible, I don't think we know, but I never believed we would get to 19 MeV. So I have a lot of confidence that the people that are doing these measurements are on a path, and we clearly will reduce the error. Whether it gets to 10 or not, I think we'll just have to see. One comment is that this measurement and almost all of the others really rely on a very large number of standard model measurements in order to improve the constraints. I mentioned, for example, that parton distribution functions are a big source of uncertainty. We can constrain those using LHC data, and as those constraints improve, those will be fed back into the W mass measurement. Okay, now how about the top? The top, life is a little harder. Top is a colored object. Unlike the W, which is a color singlet, the top is intrinsically connected to the rest of the event. So what we mean by the top mass itself is ambiguous, because one never sees a free top quark. So the definition of the mass doesn't have the same meaning as it does in the case of a colorless object. Typically, there are two definitions that we use. One is the pole mass. That's the mass that's used in cross-section calculations and is related to what we use as input for electroweak calculations. The mass, of course, depends on the scheme that's used, but going from one scheme to the other is well-defined. So the pole mass is a well-defined quantity. Now, unfortunately, the mass obtained by reconstructing top decay products, often known as the direct mass measurement, sometimes it's even called the Monte Carlo mass because it requires detailed Monte Carlo modeling and has uncertainties associated with that modeling. It depends on the details of how the top decay products are connected to the rest of the event. So a lot of the discussion of improving systematic uncertainties in direct top measurements are related to measuring enough quantities in the top production and decay so that you have confidence that your modeling of those connections and the different possibilities for that connections are well understood. The pole mass and the direct mass measurements can differ by a few hundred MeV. They don't have to, but understanding the consistency between those two is an important part of the story. It's a complicated business that will require multiple measurements using different techniques to assess the reliability of the uncertainties. So on the left-hand side here, we have a set of direct top mass measurements, again, measurements that are made by reconstructing the top decay products and finding the invariant mass. It's a rather old, many of the measurements are rather old because the combinations are difficult to do. And the reason the combinations are difficult to do is in many cases, the systematic uncertainties are correlated. In some cases, they're even correlated between the two experiments because they have to do with the Monte Carlo modeling. So the combinations are always slow compared to the initial measurements. But you can see that Atlas and CMS are in good agreement. And there's no evidence that when you look in different channels, you see significant differences in the observed mass at the top. But just as a word of warning, I've shown on the right-hand side a measurement that's pretty impressive, but also shows us that we have to be very careful. This has been shown in a preliminary form in conferences. It hasn't yet been published because we're still evaluating whether or not the systematic uncertainty quoted here properly incorporates all the Monte Carlo possibilities. So here's a kind of novel technique. What's done here is in order to measure the mass of the top quark, you look at a top that decays to a W, the W decays to a lepton, and then the top, since it's W plus B, you can look at the case where that B decays semi-leptonically and use the invariant mass of the lepton from the W and the lepton from the B as a proxy for the mass of the top. In principle, that should be an excellent way to measure the mass because it involves only leptons. You don't have to worry about understanding the energy scale of jets, which is always messy. There's lots of statistics in this measurement. Again, as you can see, it's clearly not statistics dominated, even though it's only using part of the 13 TV data. And the whole argument is how much does this dilepton invariant mass depend on the Monte Carlo modeling? If we look instead at top mass measurements of the pole mass that are obtained by looking at the cross section, which depends on the mass of the top quark, here the measurements have larger uncertainties than the direct measurements. But again, the consistency between those two is really an important part of the story. These measurements improve as the theory improves. So for example, going from next to leading order to next to leading order theory improves the scale uncertainty from 10 to 5%. So both as you get more experimental data and as the theory calculations become even more precise, the role of these pole measurements will become even more important. Okay, so let me move on to my second topic, the use of dibosons in order to understand BSM physics. And I'll begin with a brief overview. The high energy of the LHC allows for high statistics measurements of final states with 2 and even 3 bosons. I'm not going to talk about the 3 bosons here, but there are now nice measurements of cross sections involving 3 vector bosons. It's an important test of NLO electroweak corrections and N² LO QCD calculations. And it's sensitive to new physics from anomalous triple gauge couplings, which are what we see on the diagram on the right. There's no single channel that's sensitive to all possible BSM contributions. So this really is a program of measuring all the possible diboson production rates and looking for consistency. And we can combine those measurements, but only within the context of a well-defined theoretical framework, and use them in order to provide limits or observe evidence for triple gauge couplings. Although the statistics are already reasonable, the increased luminosity of run 3 and the high luminosity LHC will further improve this precision. And in particular, sensitivity to these anomalous couplings increases as you have larger invariant mass for the diboson pair. So increasing the statistics at large invariant mass, which will be possible with more luminosity, will improve these measurements greatly. Okay. Just to give you a feel for where we are right now, in this case, I took a CMS plot. So I don't always just show Atlas because it happens to be the experiment that I'm on. And you can see the measurements are pretty good. And once again, the experiment versus theory are in good agreement in most of the cases. There are a couple of small deviations, but nothing that would make you worry that there's anything going wrong. As I said, these can be turned into limits on anomalous couplings, and this just gives you an example of what such limits would look like. I'm not going to go into the details of what these things actually mean, but delta kappa, of course, as you can see, would be the anomalous coupling of the kappa for the Z bosons. So it's mainly to give you a sense of the kind of work that's being done right now. Okay, so some observations on this diboson production. All combinations of W, Z, and photon are probed. Typical precision depends on the channel, but we're seeing things in the 1 to 10% range. There's no evidence of BSM physics to date. And as I said before, combining the measurements requires a theoretical framework in order to characterize the deviations. And in fact, several such frameworks exist. And the best use of these data really require strong collaboration between the experimentalists and the theorists, both to decide what's the most appropriate framework to use and to make sure that all the measurements are combined using consistent treatment of the systematic uncertainties. One thing to warn is that these measurements are in general dominated by strong production. And of course, we expect the new physics to show up in the electroweak sector. So the next step is to really select kinematic regimes that are sensitive to electroweak diagrams and to study both single and diboson production in electroweak enhanced phase space. So what do I mean by this? Well, here's an example where we're talking about single boson production. The arguments are the same for single and diboson production. We can divide ourselves into a case where we have strong production. That's the case on the right. And from the point of view of these measurements, we call those background because we don't expect to be sensitive to new physics in those right-hand side diagrams. And cases where we have electroweak production. So for example, the diagram on the very left shows vector boson fusion, where each of the initial quarks wiggles off a heavy vector boson, and then those fuse to form a W. And so the signal we have in that case is the production of a W in association with two jets. Those are the quarks. Because the quarks are just wiggling off a gluon, they tend to go in the forward direction afterwards. So the signal is a boson together with two jets that have a very large separation in angle, one going mainly in the forward direction and one going mainly in the backward direction. And both for the vector boson fusion and vector boson scattering, the presence of these large jets separated in rapidity is the way to isolate a phase space that's has less QCD background and more strong and more electroweak production. So I won't spend much time on this. It's just an example of what some of these vector boson signals can look like, and the fact that you can get constraints on the triple gauge couplings from them. Okay, you can also get constraints on the quartic couplings. Those happen from the vector boson scattering channels. And again, I won't talk about them in detail, just to comment that such constraints can be done using the data. What I did want to say a little bit more about, and I only have a couple of minutes left, is to talk about the observation of electroweak scattering in cases where you can really see the signal most clearly. And one of these two is same sign WW scattering. The reason for that is the strong production is highly suppressed in the case where the two W's have the same sign. So the ratio of strong to weak production is much more favorable for looking at the weak production than it is in some of the other modes. And here again, you see the strong on the weak production diagrams on the left. This is not a very common process. You can see on the right-hand side, the currently published Atlas data. It's still a partial data set. The analysis of the full run 2 data is in progress, but the statistics, as you see, are quite limited. The way the measurement is done is you require 2 jets with a large separation. You enhance the electroweak signal by requiring a large invariant mass on the dijet mass, and then you look at the invariant mass of the 2 leptons. The higher the invariant mass of the 2 leptons, the more sensitive you might be to anomalous coupling. So with more statistics, one would really want to focus on that high dilepton invariant mass region. There's about a 6.5 sigma signal to observe this production, and it will be interesting to see when there are more statistics whether or not any anomalies develop. The second channel that I wanted to highlight is photon-induced diboson production. This is the case where the 2 protons don't actually fall apart, they stay protons. Each one of them radiates a photon, and then those photons interact in order to form dibosons using the 2 diagrams here. So if one asks what's the signature, since the protons stay protons and are just wiggling off the photons, you're looking for a case where in the signal, there's no additional particles other than the 2 W's, both of which decay leptonically. So you're looking for missing energy, 2 leptons, and no additional tracks. It's impressive that one can actually see that from the event display on the right. Here's an example of one of the candidate events. So because it is high pileup, there are many, many primary interactions in the same beam crossing. Each of the reconstructed ones here is a dot. The dot that has no other particles near it is the one that the 2 leptons from the W come from. And you can see there's no evidence of any other tracks near there. So understanding your efficiency for finding tracks in this very dense environment is, again, an important part of convincing yourself you believe the signal. And in the plot on the upper right, the signal here is the 0 additional reconstructed track bin. Okay, so that is all I really have time for. It just gave you a feel for the type of measurements we can do. So here are my conclusions. Outstanding performance of the LHC collider and the experiments is ongoing. There are large data samples collected, and timely analysis is underway, and techniques to mitigate pileup are in place and working. The large integrated luminosity allows precision measurements to constrain virtual corrections, top mass in many channels, first W mass measurements at the LHC, and progress of measurements of weak interaction parameters. Observation of exciting low cross-section processes such as vector boson fusion and vector boson scattering exist, and combined measurements in many channels allow us to constrain the anomalous couplings. And major advances in techniques for theory were essential for us to be able to control the uncertainties in these channels. We're still at the beginning. The current data samples are only 2 to 5% of the expectations for the high luminosity LHC, so there's a lot of exciting physics to come. And that's it for me.
Thank you, Marjorie, very much for this comprehensive talk. Does anybody have any questions? Please raise your hand. So I don't see any questions. I have a few. Concerning, Marjorie, the MW measurement, You mentioned two different types of uncertainties, the modeling uncertainties and the experimental systematic uncertainties. So the modeling uncertainties, these only come from Monte Carlo and parton showering. So
they come from, there's parton distribution functions. So as you change the choice of parton distribution, it changes the longitudinal W, and then the transverse distribution of the W, because the lepton PT changes if the PT of the W is different. So those are probably the two most important modeling systematic uncertainties for the theory modeling. And,
okay.
Yeah, and the PT is constrained by looking at the PT of the Z. And of course, since the W and the Z masses are different, you can't just use the PT distribution of the Z, but you can validate the theory corrections, which are done using resummation techniques, and use that in order to try and constrain the modeling of the PT of the W and the Z.
Right. So if I understood correctly, the way to get that number down is to have a better precision in this resummation and parton distribution functions.
That's right, because the resummation always has some non-perturbative parameters in it. And then the other way to get it down is to better constrain the parton distribution functions, which can be done using the asymmetry between the W plus and the W minus production as a function of rapidity, which can be fed into fits to the parton distribution functions. And that will also, in the long run, reduce the uncertainty.
I see. Also, just out of curiosity, you mentioned that LHCb it has a W measurement. How they do it?
So I have to admit it's a new paper and I haven't read it in as much detail, but they of course are looking mainly in the forward direction, so it's a very different kinematic range. And I believe that they still are very statistics limited. They have good momentum resolution and very good control of that momentum, because since they do B physics, calibrating their tracking is extremely important. But it's on my list to go through that paper in more detail. I think it's not yet a competitive measurement in terms of uncertainty, but it has promise for the future. And I don't know what the situation is with CMS. Presumably there will be a CMS measurement, but I haven't seen one yet.
Thanks. Fran, questions?
Yes, hi Marjorie, I'm Francisca. Just also out of curiosity, on the last slide that you show on these protons that don't really interact, but they irradiate these photons, and then you can have this really clean final state. How often does that happen?
The cross section is really tiny, but so you can see in the full run 2 data set, which is 139 inverse femtobarns, we're seeing a couple of hundred events. So it's not a handful of events, it's a measurable number. But it's clearly a small cross-section process.
Okay, it looks nice. I didn't really know about it, so good.
Yeah, and this is something that there's also been discussions about how one could do this using heavy ion collisions, because of course, since the heavy ions have large Z, the photon luminosity is much larger in heavy ions. So the energy is lower because they don't run the heavy ions as high in energy, but the photon luminosity is very big. So there's been lots of discussion about both at ALICE and at Atlas and CMS about doing 2 photon physics using the heavy ion data. And there's probably a lot of opportunities there that haven't been fully explored, because I think a lot of the people who are used to doing PP analysis haven't thought sufficiently about what you can do with heavy ions.
Okay, thank you.
Any more questions or comments for Marjorie? Sergey.
Yeah, I have a question about this the same process. You say here that this process is in this process both protons remain intact.
Yes.
How can you control? How can you control that? This
You can't. The only way you can control it is by the fact that you don't see any other particles besides the two W's. In an ideal world, you would want to do an experiment where you tag the protons using a forward spectrometer. In the old days, when you did 2 photon scattering and E plus E minus, they always used to have forward detectors, and you would have single and double tagged cases where you saw the electrons in the forward detectors. In this case, we don't really have the ability to do that right now. Perhaps with the luminosity monitors, one could consider it, but this is an untagged measurement. So that's why there's some background. If you look in the plot on the right, that purple is cases where the proton has not stayed a proton, and how much you have in that purple is to some extent dependent on the minimum momentum for which you can reconstruct tracks, because that purple corresponds to a case where you probably have a few tracks, but they're not being reconstructed because their momentum is too low. So one of the improvements they're talking about for the next version of this measurement is to push down the momentum of the tracking in order to try and reduce that purple background underneath.
Mm-hmm. But how big is the virtuality of the gammas? If virtuality is large, then this process should be suppressed by the form factors in this if the protons are intact.
I think that's right, and I don't know. I have to admit, I don't know how that is calculated. I should go back and look at the paper, but I agree with you that there needs to be some kind of a form factor there.
Yeah, because this process looks like in this process photons could easily be quite far away from mass shell.
That's right. That's right. So there must be a single and double diffractive piece to this. Right.
Yeah. Okay.
Yeah.
Yeah. Yeah. Thank you.
Does anybody have any more comments or questions? So may I just ask naively, when you mentioned this distinction for the Electroweak and Diboson channels for the, I think you were talking about the quartic interactions, and then you show your plots as a function of this ratio here, this lambda.
Yeah, so lambda is some typical, the problem is that if you're using a theory with an effective interaction, then you end up with a mass scale, the same way in the old days, G Fermi had a mass scale.
Yeah. So I was wondering.
Right, so I can't remember what they used. They probably use 1 TeV for the lambda, for the limits there, because the limit doesn't mean anything unless you say what the value of lambda is that you use.
Yeah, I mean, this is what I was going to ask.
I think they use 1 TeV.
Okay, so in principle, lambda is fixed, and these limits will change, of course, if you are thinking about a new effective field theory.
That's right, and that's one of the problems with this formalism, is because it depends on the lambda. So there are several formalisms that people have proposed. So you can, and I don't think it's fully determined which is the most interesting to use. And part of the problem is that when you don't have that many measurements, and once you have quartic couplings, there are lots of options for coupling constants. And so if you end up with a situation where you have more free parameters than you have measurements, it's difficult to do anything that's particularly insightful.
Right, but in principle, you could kind of reinterpret these bounds and try to come up with a limit on lambda, right?
Yep.
If assuming different sort of choices for the Wilson coefficients, or
Right. And I think probably this should be done in a consistent way with the discussion of Higgs couplings, because they, the techniques for the anomalous Higgs couplings are similar, and there are probably a lot more people working on the anomalous Higgs couplings.
I see. Thanks.
Mm-hmm.
Okay, if there are no more questions, Sergey, do you have additional comments, or did your hands to stay there?
You mean who?
You have your hand raised in the Zoom.
I just want to thank very much for this so interesting and informative presentation talk about new physics searches. Well, I don't have any other comments. Thank you very much.
Thank you,
Thank you for
Marjorie.
inviting me. Okay, thanks very